We're going to find all of the complex numbers that lie in this region R outside of a hexagon, take the reciprocal of those numbers, and find the area of that region. I'm going to put our hexagon inside of this circle centered at the origin in the complex plane. And here these two sides on the left and right are parallel to the imaginary axis. We're going to divide up the region outside the hexagon into two parts. The first part is the region outside of the circumscribing circle, and the second part will be the 6 smaller regions between the circle and the side of the hexagon. These 6 regions are all congruent and they kind of are shaped like this. Let's start with the region outside of the circle, which I'm calling R1. The distance between parallel sides of the hexagon is 1, so this distance from the origin to a side is 1/2. This radius forms a 30-degree angle with the real axis. So the radius is 1/√3. And we'll call this circle C1. Since the circle has a radius of 1/√3, then the magnitude of all the points on the circle is 1/√3. So we can write Z on the circle by this complex number, where theta goes all the way around the circle. Let's take the reciprocal of these points. And so the magnitude is √3. So the inverse of all the points on this circle maps to another circle with a radius of √3. Since we're interested in the points that are in the exterior of the circle, this means all the points Z that are greater than or equal to 1/√3, which means the inverse of these points reside within a circle with radius √3. We'll say that this region R1 maps to S1, and the area of S1 is the area of a circle pi r squared, or 3 pi. Now we're going to take a look at R2, these 6 other regions between the circle and the hexagon. Here it is again. We'll call these 2 points AB. This region here on the right is bounded by this segment AB and the arc of that circle. We'll see where the segment and the arc maps under inversion, and then find the area of the region between these two. So let's see, where does the vertical line that passes through A and B, where does it map? So the distance from the segment AB to the center of our hexagon is 1/2. So all the points on this vertical line can be described as having a real part of 1/2 and an imaginary part that varies over all the real numbers. Let's find the inverse of the C, and we'll get rid of the fractions. We'll get rid of the imaginary part in the denominator. Simplifying, this becomes 2 minus 4yi over 1 plus 4y squared. Let's separate this into its real and imaginary parts. We'll call the real and imaginary parts u and v, and let's see if we can find an expression relating u and v. We'll take this real part u and solve for 1 plus 4y squared. This is equal to 2 over u. And we'll substitute this in for y, and we'll take this and solve for y. Now we'll substitute this back into this equation. Now we have an equation that only contains u and v. So we'll get rid of these fractions and simplify it. Eventually, it looks like this. This is looking like a circle, so let's complete the square by adding 1 to both sides. So it looks like when we take this vertical line that passes through A and B, it maps to this circle. Let's call the center of this circle P, and it's located at 1 plus 0i, and it has a radius of 1. We'll call this circle 2. Here are our points on the vertical line, and here is the circle that it maps to with a radius of 1. Let's see what happens when we invert the points on this arc from A to B. Here's circle 1 again, and it has a radius of 1/√3. Here Z1 and Z2 are vertices of that hexagon. Z1 has a magnitude of 1/√3, and its angle here is pi/6. And so the reciprocal of this is a point 30 degrees below the real axis on a circle with a radius of √3. Similarly for Z2, the inverse is also on a circle with radius √3. This circle centered at the origin with radius √3. Let's call this circle 3. So now we're going to find the area of the points that are located between circle 3 and this circle 2, which was the inversion of the other boundary line. Let's draw these two circles. This is circle 3 with a radius of √3. Let's call these points A and B again. Again, they're 30 degrees above and below the real axis. And then we have a circle with radius 1 with a center at 1 on the real axis. So it's going to look something like this. This is circle 2. This is the center point P. So our region 2 is going to map to S2, which is this region between these two circular arcs. We're going to find the area between these two arcs that pass through A and B, and we're going to multiply it by 6. So the area of S2 is going to be 6 times the area of the shaded region between these two arcs. To find the area of the shaded region, we're going to find the area of sector AOB that's contained in this black circle C2. I put sector in quotes because the angle is actually an inscribed angle, not a central angle, so it's not a true sector, but I'm just going to call it this for now. Then we're going to subtract out the area of this true sector AOB on circle 3. That's the green circle here. Let's drill down on circle 2 again. It passes through point O and it has a center P. To find the area of this so-called sector, I'm going to find the area of this true sector of the circle, APB, and then add in the area of these two congruent triangles. We have APO on top and BPO on the bottom. We know that angle AOB is 60 degrees. That's the inscribed angle, so the corresponding central angle APB is twice that, or 120 degrees. So the area of sector APB is 1/3 the area of circle 2, which has a radius of 1, so that's 1/3 pi. Now let's find the area of this triangle APO. We'll find the distance from O to P is the radius of the circle, that's 1. We have triangle OAH is a 30, 60, 90 triangle. So the distance from A to H is √3/2. So the area of triangle APO is 1/2 base times height, or √3/4. We'll fill in these areas and 2 times the area of the triangle. So the area between circle 2, between points A, O, and B is pi/3 plus √3/2. That takes care of this first part. Now let's find the area of sector OB on circle C3. This was our circle centered at the origin with radius √3. This angle is 60 degrees, so this is 1/6 the area of the circle, or pi/2. So S2 is going to consist of 6 of the area of these shaded regions, which we find by subtracting this sector from C3 from this so-called sector from C2. This simplifies to 3√3 minus pi. We'll add this to the area of the other region that we found. Here it is, S1 was 3 pi. This simplifies to 2 pi plus √27, and the problem asks for A plus B, and our answer is 29. If you'd like me to solve any other math contest problems, please leave them in the comments.